Okay, I'm going to go over the problem that I gave at the very end of class, or if you didn't get it at the very end of class, here it is. I'm going to go over it real quick. You'll pause the video, hopefully try to do it entirely on your own, and then you can kind of watch the video if you want, or I can just tell you the answer towards, if you can skip to the end and see what the answer was, see how you did. Okay, so in this situation, first hour decided this person is called the John Football. That's the name of the individual. The importance of that is none. There's no importance of calling him the John Football. It is entirely up to you what you call the individual. Call him Steve. Call him Larry. Call her Denise. I don't care. Anyway, so Denise, Larry, Steve, John Football, whatever, is traveling to the left at 4 meters per second. They have a mass of 150 kilograms. This is rather large. That would be a 330-pound person. And then they get hit to the right with 200 newtons for 1.7 seconds. And our job is to find the final velocity. With that information, a quick hint, don't forget that we are dealing with vectors again, so we do have to assign direction accordingly here. I'm going to go ahead and say right is positive, which makes sense. You can certainly make left is positive as well. It's entirely up to you. I see the value of both, but I would pause it here and see how much of this you can do, and then we can come back and see if you want to follow me or just skip to the end. And I assume you've paused and you didn't just keep watching video. But again, if you want the answer, skip to the end. If you want to see how to do it, here's what we do. We are dealing with the impulse momentum theorem. So there's the impulse momentum theorem. Okay, and the impulse momentum theorem, similar to the work kinetic energy theorem, sort of transforms a little bit because we have, like right over here inside momentum, actually a couple values, and we can kind of trade it out from there. So the easiest way, and you can feel free to skip ahead to all of these or any of these. I'm going to show you all of them real quick. So change in momentum would either be momentum final minus momentum initial, or each individual momentum would be mass times velocity final. That would be this momentum minus mass times velocity initial. That would be that momentum. This one obviously is going to be the one we're using because we want to get V final. Or if it matters, you could factor out mass of this, and it's also equal to mass times change in velocity, because that would be mass times Vf minus Vi. And so I would always start here, but which one you go to, I don't need you to show me the steps that I just showed. I'm completely fine with you kind of going to the next one that is best suited for you. So we'll go ahead and write that here. Sum of forces times time equals mass times Vf minus mass times Vi. And we can see here is momentum final, and here's momentum initial. Okay, the person is running at the very beginning, so they will have a momentum initial. And we're pretty sure they're moving at the end because it asked for this, but we can calculate that here in just a second. So for the most part, this is just algebra, right? We are looking, this is the net force. We should do a force diagram here, but it's going to be pretty easy because since it's just a net force diagram, all we really got to do is concern ourselves with the basic direction, and we know they're getting hit to the right. There it is. There's the net forces. Are there force normal up and force gravity down? Sure, but those are canceling. This is probably the hit from some other individual over here, but we'll talk more about that tomorrow. Now, direction. And the beginning of this problem, if I were you, this is how it would probably look if out of the book. But if I were you, I would write net force is, for example, positive 200 newtons. That signifies you're right because of this thing I said here. Obviously, if you had said left is positive, that would be negative. And this velocity initial over here should in fact be negative 4 meters per second because they're moving to the left. And obviously those two would be switched if you assign the opposite direction. From here, we just do some algebra. I'm trying to get this guy, so I'm going to go ahead and add the right entire term here. So this should be mass times Vi plus net force times time equals mass times Vf. And simplistically put, that says initial momentum plus the change of momentum equals the final momentum, because of course it should. So this should be mass times Vi plus net force times time all over the mass, dividing that guy out to get velocity final. And mass is 150 kilograms times velocity initial is negative 4 meters per second, which means this initial momentum was negative 600. Not an important step, but come on. You're not going to do it for me? Where are you? Sorry. learning the board. Plus, net force is 200 newtons times the time of 1.7 seconds. And that is divided by 150 kilograms. So this should be, like I said, this side is negative 600. This right over here should be positive 340, right? So that should be negative 260 divided by 150 should be negative 1 point something. Should have had that checked ahead of time. Negative 600 plus, pretty sure that's 340. Let me make sure. Okay, divided by 150. We should get an answer of negative 1.73 meters per second. Makes sense that it's still negative because it was a big old individual up here with that 330 pounds there. So you hit him. You hit him going to the right. He slowed down, but he's going to keep on trucking because he's a big individual. So that's our final answer, negative 1.73, or you could also say 1.73 meters per second left to signify that vector component of direction. All right, that's how to do the problem.